So far, we've talked about a bunch of definitions of gases, and we've gone over some relationships when we make things change. So let's combine those different relationships to come up with a law we're going to call the ideal gas law. And related to time, this was discovered in 1834 is the date I've got for it. So again, this is newer. This is compared to, let's say, Boyle's law. That's over 200 years later, but it's still relatively old compared to other topics you're studying in chemistry. And note, I'm not trying to get you to memorize a bunch of dates. I just try to give some perspective because I know sometimes we get away from that part, and that can be easily forgotten. So if we combine all the relationships we've been learning about, what we discover is that we can come up with this equation. PV equals nRT. And everything but R should be familiar because we've gone over those. So this is going to be a pressure. And we're specifically, for this class, going to measure it in atmospheres. I will note, when you see this gas law in another class, you can use different units for these, but it's going to change what this thing called R is. So R is going to be based on what units you use. We are going to use it with a pressure in atmospheres, a volume in liters. We're going to have N be, it's our number of molecules, and it's going to be in moles. So it's the number of gas molecules. And then finally, T is going to be our temperature in Kelvin. Temperature, which I may or may not have spelled right. Which I can just claim because I'm poorly right it. Maybe you just misinterpreted my letter if I'm wrong. I think I got it okay, though. Yeah, I can spell temperature. See, I don't even have to have a spell check. So that's our ideal gas law. So then, hey, wait, you just told me this, but what's this R thing? So R is what we call, it's going to be the ideal gas law constant. So this is going to be in units. It's going to be 0.0821 liters times atmospheres per mole Kelvin. It has all the units in it. This is the numerical relationship between these four units with each other. So if you know three of the four, you can always find the fourth using this constant. This constant is the relationship between these different variables. So if you know pressure, volume, and temperature, you can find N. We're going to use that one a lot because we like knowing how many molecules we have, because then we can use balanced chemical equations. But you can do that with any of them. You can have PV and N, and you can solve for T. You can do this with any particular relationship. You will use this law a lot. And this law comes from using Boyle's, Charles, and Avogadro's laws, and combining those relationships helps to why we actually are able to figure out this law. So now, let's look at what we can do with our handy-dandy ideal gas law. So let's say we've got some material that we know about. Suppose that we're going to have Dr. Slattery. I like working with him. He's going to have some gas in his lab. Suppose Dr. Slattery has a container that contains 0.845 moles of nitrogen gas, let's say, at a slightly elevated pressure, but not too high, a pressure of 1.37 atmospheres, and a temperature of 315 Kelvin. What would be the volume of this gas? So we want to know how big this container is, for example, let's say. What would be the volume of this gas? So even though we have not directly done this, you have done enough manipulation of equations that I think you can probably figure this out. It's purposely been kept in units that you know, that are the correct ones. You don't have to do transitions. We'll practice that later. And just as a reminder, that R is 0.0821 liter atmospheres per mole Kelvin. So I want you to try pausing my video and manipulating this equation and solving for volume. So give it a try. Okay. So if we've tried that, so we're going to start by getting volume by itself. That means we divide both sides by pressure. That's just your pressure, not an R. So we have volume equals nRT over P. And so it's important to make sure we use the right units. So with these problems, one of the first steps will be, let's check if our gas law and our units match. So N is moles, that matches our constant. Temperatures in Kelvin, that matches what we're given. Pressures in atmospheres. In most problems, you're probably going to have to convert at least one of these. You might be given grams, because I could have told you how many grams of nitrogen he had instead. You could use the molar mass to convert it to moles. And you might even have to do all three. You might have to do Celsius to Kelvin and torr to atmospheres. So just make sure to check that and don't just ignore the units. I know that's something that can get easy to get in the habit of, oh, the units are just right, we just won't worry about them. I'll just write the right unit at the end and all will be fine. So make sure to check on that. You do have to do that part. So if we plug our values in, we have 0.845 moles of gas. He has 0.0821 liters times atmospheres per mole Kelvin for the constant. Our temperature was 315 Kelvin. And then we're dividing that by a pressure of 1.37 atmospheres. And when we check our units, we can see that atmospheres would cancel, moles would cancel, and Kelvin would cancel, which would leave us with liters. So then we just have to plug these in. So we have 0.845 times 0.0821 times 315 divided by 1.37. So there, I'm going to get that the volume of this container, there's my pen, had to be, that rounds up, 16.0 atmospheres. I got 15.95 on my calculator, just noticed it. I only have 3 sig figs, so it'll be 16.0 not atmospheres, just kidding. Liters. Sorry if that bothered you at first. But this is the trick. Learn your ideas well enough and you can make a quick correction rather than writing 16 atmospheres on your test, moving on to the next problem and losing a point for that. So these problems by themselves, this is what you'll be doing. You're given 3, solve for the 4th. I do think these are a type of problem you can get pretty good at pretty fast, but if this is really uncomfortable, I do suggest practicing a few. Now, we will later have ones where this is a point and then you have to do some more. We'll have to use it. We'll connect it to a balanced chemical equation and do some more stuff. That'll be in some videos later, probably next week. But just know you should be able to do these. There's one other idea I want to connect to this that'll be related to how we do problem solving. So we'll do a bunch of these. We'll practice them in class plenty. And if you are watching this from some other source, I suggest there are plenty of practice videos with just go find practice problems with ideal gas laws. Try them. Make sure you're doing okay with them. And just practice moving the numbers around. So the other thing I want to mention here is something we call standard conditions. So standard conditions are the idea that we've set up some numbers that we're going to call STP, which means a scientist can tell you, oh, these were made at STP. This is useful, for example, we'll have tables of constants, for example, where someone's measured some particular information and you want to know about it, and they can tell you, oh, that was done at standard temperature and pressure. And so that's a way of telling you what is the temperature and what is the pressure. Now, I'm going to point out at least one of these, while it is the standard we've agreed upon, it may not sound all that standard. So STP is a temperature of 273 Kelvin, or 0 Celsius, and it is a pressure of 1 atmosphere. Now, I don't know about you, but my chemistry lab is probably not going to be at 0 degrees Celsius unless I'm working in a cold room for some reason and I need to actually work at zero, at a freezing temperature. But if not, and even then I'm probably going to work at 3 or 4 Celsius so I can use water as a solvent, not have it be ice. That means that when someone says STP, it's not quite standard. Now, there are some times where it's close enough and we can go, okay, at my 10 degrees is close enough to your 0, but we also may have to adjust for it. So this is our STP. And you can use that idea I talked about earlier, the P1V1 over N1T1 equals P2V2 over N2T2. You can make adjustments based on, oh, I know my pressure and temperature, and I can compare it to STP and see how the other numbers would change and see which one's set. Like if my volume is a beaker, or let's say a flask, a closed flask. My closed flask isn't going to change volume. If it changes volume, it's literally going to break because if it expands or if it shrinks, it'll also break. It's a rigid object. So if you have a rigid container, that's a way of saying volume's constant. Or maybe it's a closed container, so that means the moles can't change. So actually, if I've got a closed flask, I wouldn't be able to change I would have to change either pressure or temperature to be different, or else literally the flask would have to break or would have to somehow deform itself. So depending on the container you're working with, there can be rules of you have to think through what's going to be constant versus what's going to change. So if I have a balloon, well, its volume is flexible, right? We know that's one of the cool things about balloons. I can go and blow them up. And then once I've tied it up, well, no new gas molecules. So the volume of the balloon can change and shrink. But if I've got a rigid container, that volume can't change, but other things can. So this will let us make those changes between, well, I know what my measurements are at this temperature at 25 degrees Celsius. Let's convert it to STP and see what the measurement would be there. So that is a term we will use sometimes. And we'll also just tell you, oh, this experiment was done at STP. That's a way of telling you the pressure and the temperature without having to explicitly state it. You'll also see it, and so that's just good to keep in mind. Let's see. And for my last idea, I'm actually going to break it off into a separate video. This one's kind of short, but I think that's okay because what we're going to do next is we're going to talk about density of a gas. And I think it'll be just a little bit too long, so we're going to stop here.